Suppose I know that the value of an investment portfolio at time t, where t is in years, and the value is given as capital P, which is a function of t. Suppose it gains 8% per year compounded continuously. Now, suppose that I wish to retire on this investment portfolio, and I want to continually be able to take out $40,000 every year from the account to live on. I want to be able to do that for 30 years, so maybe from when I'm 65 to 95 or something. How much must the initial value of the portfolio be to allow me to withdraw $40,000 for every year for 30 years without running out of money? Okay, so let's set up this equation. So we're given that this investment is given by capital P, and we're told that the rate of change of capital P, of our investment value, is equal to the rate in minus the rate out. So now we have to look at the question and determine what is the rate in and what is the rate out. Well, how much money is going into the account? We're not depositing anything. All that's going into the account is the interest. So the amount of interest that's going in is 0.08, because that's 8%, times the amount, times P. And I subtract out how much per year is coming out, 40,000. Okay, so this is the rate of change of my investment. So obviously the rate of change of my investment value is how much is going in minus how much is going out. And if I rearrange this equation, I end up with this following differential equation. dp by dt minus 0.08p is equal to negative 40,000. And this is a first order linear differential equation. It's a differential equation because there's a derivative and an equal sign. It's first order because the unknown function p has a derivative, and the highest order derivative is the first order here, first order derivative. So it's a first order differential equation, and it's linear because the only other place that p shows up, the unknown function p, is here, which is p to the power of 1. So this is a first order linear differential equation, so we're going to use the method of integrating factors to solve it. So the first thing we need to do is identify what our functions are. So this little piece here, the negative 0.08, this is little p of t, and the negative 40,000, this is little q of t. So knowing this, I can go and calculate the integrating factor, which is equal to e to the integral of little p of t dt, and that's e to the integral of negative 0.08p, oops, not p, little p of t dt, and this is e to the integral of negative 0.08 dt, which is equal to e to the negative 0.08 t. Okay, we don't have to worry about the constant when we're doing our integrating factor. So multiplying our entire differential equation by this integrating factor, what I get is e to the negative 0.08t times d capital P by dt minus e to the negative 0.08 times 0.08p equals negative e to the negative 0.08t times 40,000. Okay, so all I've done is multiply our differential equation by our integrating factor. What that does for me is it makes the left-hand side exactly into a product rule as if we recombined it. So the left-hand side is actually the derivative of e to the negative 0.08t times capital P. Okay, if you do this derivative, what you'll find is using the product rule, you get this this left-hand side. The right-hand side stays the same. I'll just rearrange it a little bit. Negative 40,000 e to the negative 0.08t. Now what I'm going to do is, to get rid of this derivative on the left-hand side, I'm going to integrate both sides with respect to t. So doing the anti-differentiation, on the left-hand side I get e to the negative 0.08t times p. And on the left-hand side, I get negative 40,000 divided by negative 0.08 e to the negative 0.08t. So that's just taking the antiderivative of the left-hand side. There will be a constant on each side, but I'm just going to combine the constants on the right-hand side into one big constant plus c. Negative 40,000 divided by negative 0.08 is actually 500,000. So if I divide both sides by the e to the negative 0.08t, I can isolate p. Capital P is equal to 500,000 plus this constant e to the 0.08t. Okay, so this is our value of a portfolio at a given time t, but we don't know the value of this constant here. So what other piece of information are we given? We're given that after 30 years, we want the amount of our portfolio to be 0. So after 30 years of doing this, we want the portfolio to be 0. So P at 30 years for our equation is 500,000. Oops, write that a little bit neater. 500,000. Plus C e to the 2.4. So this is what happens when you plug in t is equal to 30. And what we want is we want that to be equal to 0, because after 30 years we want our value of our portfolio to be 0. So solving for C, this means that C is equal to, you bring the 500,000 to the other side, and you get negative 500,000 e to the negative 2.4. After you bring the 500,000 over, you divide both sides by e to the 2.4, and you get this value for C. So at the end of the day, P of t, the value of this portfolio at any given time t is 500,000 minus 500,000 e to the negative 2.4, so that's C, times e to the 0.08t. Okay, so the question is asking how much must the initial value of the portfolio be? So how much at time equals 0 should the portfolio be valued? So what we're going to do is we're going to plug in t equals 0 into our formula, and we get 500,000 minus 500,000 e to the negative 2.4. And then when you plug in 0 for t, you get e to the power of 0, which is just 1. And if you calculate this, this is approximately equal to $454,641. So the initial value must be $454,641.